In a previous lecture, we discussed how we can describe a single variable. There are different ways to describe this. We can say that, the mean is here, the median is here, that the spread is this, and that the variance is also a measure of spread, or maybe it looks like that. Now, what we want to do in this lecture is discuss how different variables relate to one another. And so one way that we do that is through something called covariance. Recall that our formula for variance is something that looks like this. This is going to be the variance of x. And if I were to ask you, how would you want to introduce another variable here? Another way of thinking about the variance equation is this is how x moves against x. But if we wanted to say, what is the covariance of x and y, how would you want to change this equation? And I hope that it becomes pretty clear that we would just extend out this little squared sign here to get our covariance. So instead of just comparing the way that x moves against x, now we're going to compare how x moves with y. And so that's covariance. Now, covariance has some really nice properties in that it will tell us how x and y are moving together. But one big limitation of covariance is that it does not give us any relative importance. And by that I mean these relationships in this example that I give over here on the left. So in case 1, we have study hours with x equal to 5, 10, 15, 20, and 25. And we have test scores y equal to 50, 60, 70, 80, and 90. In case 2, we have the same x, but we have an order of magnitude higher y. Now the relationship is actually the same, but the covariance is going to be very different when we go ahead and calculate it out. So that presents an issue with using covariance. It's not a standardized measure. It's not a relationship that we can compare across different examples, or even within the same example where it has the same relationship and it just doesn't quite match up. And so we have the standardized measure of covariance called Pearson's correlation coefficient. Now, Pearson's correlation coefficient essentially takes this equation, covariance, and we're going to divide it by this term on the bottom. And I'm not going to draw this out. You can look over here on the left. So we can see this equation over here where we include this denominator that squashes any covariance that we're going to get between -1 and +1. A +1 gives us a perfect positive linear relationship. That's that example over on the left where if y is always increasing, x is also always increasing. Alternatively, we can get a -1, Pearson's correlation coefficient, in which case this is saying when y is increasing, x is always decreasing. I don't know why they chose to show the y variable on the x-axis over there, but I hope that makes sense. 0 indicates that there's no linear relationship at all. It might look something like this, where half of the time they seem to be have a negative linear relationship, and half the time they seem to have a positive linear relationship. And so that would be an R of 0. Okay, so that's Pearson's correlation coefficient. Now, Pearson's is really great, and it's actually, if you were to just run the correlation function within pandas, you're going to be running Pearson's correlation coefficient under the hood. This is the usual one that people will use. However, it's not always the best one to use. Pearson's assumes a linear relationship, but we don't always want to assess a linear relationship. Sometimes a curve that looks like this, where it's just always increasing. So as we increase in x, we always increase in y as well. This is called a monotonically increasing relationship, and sometimes we want that to be perfect. Sometimes we want to give that an r equal to 1. If we just ran Pearson's on this, these don't fit on a straight line. And so we're not going to get a perfect correlation. And so we need a different way of measuring the way that these two variables move together, because we want to recognize that this is a monotonically perfect relationship. One way that we can do that is something called Spearman's. And so Spearman's will actually look at the rank of each measurement of x and each measurement of y. And it will say, as long as you are increasing in x, as long as you are increasing in x and also increasing in y, we're going to say that's great. Let's put this into context a little bit. So if I ordered my x-axis, because that's what we do, and I said, what is the highest value on the x-axis? Let's start with the lowest. What's the lowest value on the x-axis? It's this one, right here. If I looked for the lowest value on the y-axis, it would also be this one. So we get a pairing of ranks, 1 and 1. Now if I go over here and I look, okay, what's the second lowest value on the x-axis? Well, that would be here. Second lowest on the y-axis, also here. And hopefully you can see that we're going to be paired all the way up. As our rank increases on our x-axis, our rank on our y-axis also increases every single time. This would receive an r equal to 1. Okay, so this example over here is a little imperfect, and I apologize for the maybe some of the confusion that this causes. But I want you to re-look at this example with this ranking that we just talked about in mind. The green is the rank of each of these different values. When we see a mismatch in the rank, our Spearman's correlation coefficient goes down because it's no longer a perfectly monotonically increasing relationship. Okay, so I hope that was a quick crash course in correlation coefficients. Please let me know if you have any more questions, and thank you to the student who requested this video.